right, we're ready to go. Jeff, this is not responding to anything I do.
Froze up big time.
Yeah.
I get nothing here. Yeah. It was okay last time. What's going on? I have to do a full reboot on that guy. I guess today, if you can just point with your mouse
Okay.
to the slide, because
Sure.
this is still working and I'll be able to still see them.
Okay.
And they'll still display.
Okay.
We're losing annotation is in essence.
All
So I
right.
have to do a reboot on that whole box.
And this is working, huh?
Oh yeah, that's fine.
Okay. All right, so who just came in? Warren. There we go. So I handed back the homeworks today, and I guess the big news is that, of course, we have exam tomorrow. So I think everybody did fine on the parts of the homework that were related to material behavior, and that was for practice in some sense. The idea was for you to see the kind of questions I ask and see if you could work with the material behavior that I gave you. The last three problems, which were a little tougher, I feel I was gentle in grading them, but I would like to see better performance than what I saw on those. The people who came to see me did much better on those. So maybe there were some issues related to exactly what was I asking and how do you formulate those kind of problems. But in general, those problems 6, 7, and 8 represent the meat of the types of behavior that I'm after in the section that we just finished. So I want to talk a little bit about that before I go on with what I've been lecturing on. And I also brought with me last year's exam so we can look that over. Okay, so just to remind you, number 6, which was problem 7.7, was to finish the Poiseuille flow in a tube problem. The problem was basically solved in the textbook, and then I also solved it again in class. So I really just needed you to do the remaining calculus and apply the boundary conditions on that one. The last problem, axial annular flow, was another flow problem, and it needed to be done in cylindrical coordinates and then apply the boundary conditions. Now, I'm going to ask you to do such a flow problem on the exam tomorrow. It'll have to be a fairly straightforward one or a part of one because they are time consuming, but I am going to ask you to do one. So we need to be clear on how to apply the generalized power law model, generalized Newtonian fluid model in these kind of flow problems. The problem 7, which was 7.14, was prediction of a material function. And what I'm hoping that you're seeing over the course of the last few weeks is that we're using constitutive equations for two purposes, and they're represented by those last two problems. One purpose is to predict material functions, and the other purpose is to calculate flow problems. So you just need to be able to switch between those two ideas, and then we'll be good. So whenever we're predicting a material function, we already know the velocity field, and we just always start with the velocity field because that's part of the definition of the material function, and we move forward trying to calculate the stress. Once we have the stress, we can predict material functions. The other starting point is when I'm asking for a stress to be calculated, or a velocity, in which case we start with the mass and momentum balances. So I think what I'll do is I'll start with this exam from last year and see how you react to it. And that way, I hope for a greater success tonight as you study, and then tomorrow when we actually have the exam. So this was the exam from March of 2005. And let's see if you can answer the questions. I mean, don't be hesitant now out of fearing that, oh, you know, I'll show my ignorance. It's more important that we settle what I'm asking for and what's the logic behind it so that you can do a better job on the actual exam. So question number 1 was, please explain why tau 32 is 0 in shear flow, no matter what material is flowing. Okay? So please explain why tau 32 is 0 in shear flow, no matter what material is flowing. Now, ask me questions if you don't know the answer, and we'll discuss it. Let's do our internal thought processes.
Is that 3-2?
Tau 32.
Because there's no flow in the 3 direction in your shear because you have the wide plates assumption.
So what you're coming to are issues that we usually deal with when we're solving for velocity field. So usually when we're solving for velocity field, we will say, well, the flow's in one direction and maybe it's wide. And we'll use those facts to simplify, say, the velocity vector and then the Navier-Stokes equations for Newtonian fluids, or gamma dot for non-Newtonian fluids. And so that's all true, but this question asks, no matter what material is flowing. So we don't know the constitutive equation of this material. So knowing things about the velocity, in that sense, you know, wide flow and unidirectional, not going to be helpful when we're asking about the stress tensor, no matter what material is flowing. But it is related to what you said, Carl, but I want to go in a slightly different area.
Is it because 3-2 is velocity, it's a change in velocity with respect in the same direction as the respect that you're driving to? Like it would be del Vy over del Y?
No, but it won't be actually. Tau 32, for again, if we knew the constitutive equation, if it were, say, Newtonian, tau 32 would have partial V2 with respect to x3, so they would be mixed, and partial x3 with respect to V3 with respect to x2. So actually, this is a tricky problem for you, and I never intended it to be. I intended it to be an easy one, and this is why I wanted to go over this kind of thing.
Just because of the geometry of the flow?
Yeah.
What are you looking for?
Yeah, it's related to the geometry of the flow. Can you be more specific?
Well, because it's just not, the stress isn't in that direction, and the tension in that direction.
What is the word? Unidirectional in this case. It's related to that. Do you remember that we did this calculation where we talked about the symmetry of the flow? So the clues in the question are shear flow. So shear flow, we actually have a definition of shear flow. Shear flow has a velocity vector of v1, 0, 0. Okay? The flow is in the one direction. And we also said that shear flow is sigma dot of t x2, 0, 0. So the way I look at this back from my school days when I would take exams is, especially, in fact, when I teach the sophomore class in chemical engineering 2110. You're all well beyond that class, and so you're all able to solve chemical engineering problems. But if you go back and tutor a junior colleague, what you'll notice with these sophomores who are just starting out is that they can read a problem and then it'll be like nothing went in their head because it just has no meaning to them. They don't pick up on the key words like even split or 20% goes overhead or the reaction goes to completion. Those little words, or saturated feed. You know, it took you a while as new engineers to learn to key in on those phrases that say so much. Oh, saturated feed, I can look that up in the steam tables. Oh, even split, that means that if Q goes in, Q over 2 goes here, and Q over 2 goes there. You immediately translate those clues into math, which you can then use to solve. And that's happening now, too. The presence of this word, shear flow, means this is the case, okay? That the velocity is only in the one direction and that this is the velocity vector, okay? And I'm asking, please explain why the tau21 from this flow is equal to 0 no matter what material is flowing. And that refers back to our discussion of the symmetry of this flow. We talked about in class that this flow, which is a linear velocity profile in the one direction, is symmetric. And when we rotated it by 90 degrees, do you remember we did a calculation where everything changed sign? And because everything that had a 3 in it, when it changed sign, we got negative equal positive. And so all of the stress components, we wrote them two different ways, one with a coordinate transformation and one with the symmetry transformation. We found out that we could write in shear flow that the stress tensor in shear flow, even for the most complicated fluid on the planet, would have this simple form. This is one of the main conclusions of our section on ideal flows, on our standard flows. The main things that we got out of the chapter on standard flows were that shear flow has a stress tensor we can simplify like this, and elongational flow has a stress tensor that, without saying anything about the material, we don't have to say Newtonian, we don't have to say power law, we don't have to say anything about it. We know that if we impose these flows, the stress tensor cannot be any more complicated than this. And that the answer then to problem 1 is, tau32 is 0 because of the symmetry of the flow. It was our ability to conclude these simplifying features of the stress tensor that allowed us to define all these material functions in the first place. So when we do, like for instance, steady shear flow material functions, we know that we only have to deal with tau21 here, tau11, tau22, and tau33. Those are the only ones we have to deal with because we went through the effort of showing that by symmetry there is no tau13, tau31, tau23, and tau32. Okay, so to me, that's an important conclusion. If I were going through and studying the chapter on standard flows, that would be one of my, I key that as one of the major things that we determined in that chapter, and that's why I put it on the test 2 years ago. So when I graded that, I was looking for the word symmetry. Okay, so number 2. So these would be the problems based on material behavior, okay? For a typical long chain entangled polymer, please sketch shear viscosity as a function of shear rate on a log-log graph. Please be sure to label your graph. So can you do that? Can you sketch for me shear viscosity as a function of shear rate? Somebody. Right, so plateau and then thinning, and then what are my axes?
Log of your
viscosity.
right?
Viscosity, and then the other one being log of your shear rate.
Right, so log of viscosity versus log of shear rate. Typically, it looks like that. Okay, so that one, free points, right? That one's easy.
Would you want multiple molecular weights for that? Or?
Well, for this one, I just asked for a typical long chain polymer. So in that case, I just wanted one. Be sure to label your graph. So if you had left off the log part, I would have probably objected slightly. Okay, part B. For a typical long chain entangled polymer, sketch small amplitude oscillatory shear material functions log G prime, log G double prime versus log frequency at low values of the oscillation frequency omega. So G prime, G double prime on a log-log graph. This is on our material sheet also.
Would it just be the terminal region, so it's just linear with the 2 and the 1?
Right, so which one's which?
G double prime 2?
G double prime is 1. 50-50 chance. Yes, you're right, Carl. It's in the terminal zone. So again, I would want you to label log G prime, G double prime versus log frequency. I don't know how you're going to remember this per se, but we looked at the whole curve, which was a plateau, a TG, a plateau, and a slope. This, for G prime, this is a slope of 2. And then G double prime, slope of 1, a minimum, a rise, and a turnover. So all I really wanted was this region. So you could have also written for me log G prime, G double prime, log omega 2 and 1. That would have worked also. Okay, the third one. For a typical long chain entangled polymer, which is larger in absolute magnitude, the first normal stress coefficient or the second normal stress coefficient? Now, when we've been predicting them, they've always been 0, but I've shown you some plots of them before, and we talked about the relative magnitude of these two. Well, if you don't know it, you don't know it. You haven't studied yet. The psi 1, I think I have some in the lecture today. Here's one of our fluids. It has a psi 1 that's quite large. Here's psi 1, and psi 2 is about an order of magnitude less. So they're in the order of the 1 and 2. 1 is much bigger than 2. The psi 1, the first normal stress coefficient, is pretty readily measurable. Psi 2 requires a PhD to measure, basically. It's a very complex measurement, not standardly done. Okay, so maybe those questions are a challenge in the sense that even though we narrowed down that chapter to just 8 pages or so, big handwriting, there's still a bunch of stuff on there to learn. So I'm not planning on being unfair. So tomorrow, if you think I've asked something unfair, you can ask me during the test. I'm not planning to ask you about details that we haven't discussed too much. But we have discussed this plateau, for instance, in the homework. And these slopes are going to come up in lecture either today or Wednesday, because those are the slopes we can predict in the Maxwell model. And of course, we've discussed this flow curve quite a bit, and you showed that that was the case by being able to readily answer it. And then we have discussed some of the details of this curve, like if this is more broad like that, what does that imply? Yeah, broader molecular weight distribution. Okay, so this is a more narrow material, and this is more broad.
So you're talking like the dispersion, right?
Yes, more polydispersed. And if I asked you to sketch the startup material functions, what I'm looking for is the idea that it takes some time for it to grow. So something like that would be acceptable, or something like that would be acceptable. And another graph that I think we've looked at in the homework quite a bit is zero shear viscosity versus molecular weight, which looks like a hockey stick. So I'm going to try to only ask what I consider really the key things, and that's why we narrowed it down to what was on that sheet. Okay, number 3. What is gamma dot, the scalar magnitude, not the tensor, equal to for steady shear flow and for steady elongational, uniaxial elongational flow? You do not need derivations for full credit, it says there as well. So this would be another case where the key phrase there is steady shear flow. Steady shear flow, as always, has a known velocity profile. So we've done this magnitude a bunch of times, and so again, in my view, this is a giveaway question, okay? So if it's not, then we should address it now.
Steady
Shear?
here is it 2 times? Is it 2 times that?
And the other thing,
Gamma dot?
Gamma dot? Or because I think we actually did like our homework problem, didn't we? Do it for that.
It comes up every time we do
Yeah,
a prediction.
yeah.
What's gamma dot the tensor for shear flow? Steady shear flow.
0,
this
gamma.
Right. 0 gamma dot naught. Okay, gamma dot naught. When we're talking about steady, again, I'm going back to this engineering problem-solving business. When it says steady shear flow, it has to be this velocity vector, and sigma dot is equal to this constant. So this is del V plus del V transpose for this particular steady shear flow.
Now you take the magnitude of it.
Yeah.
Right, the magnitude of that is,
Square root of gamma dot double dot. Yeah.
and we've done it before, it
Yes.
comes out to
gamma dot.
gamma dot naught.
Yeah.
Okay, that's why I said you don't need to do all that math on because we've done it before, and I presume that we could just write it down. If you want, you could go through and do all the math just for confidence, but the idea is we've seen this a bunch, and therefore we should be good on this. And how about for uniaxial elongation?
Isn't it just square root of 3?
Square root of 3 times gamma dot.
Exactly, square root of 3 times epsilon dot naught.
Yeah.
Okay, so this is the one that has, the flow is in the epsilon dot naught direction here.
Two.
So this one, right, so this one's 2 and this one's minus, and this one's minus. Now, when we're not doing steady flows, these are the sigma dot, you know, or the epsilon dot with the time in it. And then it's not steady. There's a time dependence to those flows. But in the steady flows, there are these very, very simple forms. Okay, so those were the first 3 problems. They were meant to be, let's say, complete in coverage in some sense, but not too difficult. Okay, not too difficult. And so that's 45 points. All right, then there's two more problems. Okay. Problem 4. We decide that for some flow modeling calculations, we would like to use the Herschel-Buckley model, which is a generalized Newtonian fluid model that contains both shear thinning and a yield stress. The viscosity function for this model is given below. So if you look at that viscosity function, compare it in your mind to Newtonian. Newtonian would be eta of gamma dot equals a constant, mu. Or compare it to the power law model. The power law model would be eta of gamma dot equals m gamma dot to the n minus 1. So it's a little bit more complicated than those. It's got m gamma dot to the n minus 1, but then it's got another term, tau naught over gamma dot. It's a little bit more complicated. All right, so this is actually a material that has a yield stress and shear thinning. Okay? In this model, tau naught, m, and n are 3 parameters of the model. They are constants. So parameters of the model can appear in any answer you would give because they are part of the model. You're predicting the model in terms of those parameters. What are the material function predictions of this model in startup of steady shearing? The kinematics and material function definitions for startup steady shearing are given below. So these are the same material functions that we've seen before on my, let's see if I've got it here. I don't have it on this, but you know, it's like this slide that I'm showing here for steady shear flow, only the one for startup. The difference being that there's this time dependence to the sigma dot. And then we have these usual predictions for eta plus, psi 1 plus, and psi 2. Okay, so what are the predictions? If you're stuck, think back, how would you do it for the Newtonian case or the power law case? And then see how this is different.
Well, you have to go ahead and develop the stress tensor.
Right?
So for GNF, the stress tensor is just going to be the function for the viscosity times the shear tensor. You just have to.
Right. So we're going to, in order to make the prediction for the stresses, we're going to construct the constitutive equation. And this is a generalized Newtonian fluid. Generalized Newtonian fluid is tau equals minus eta gamma dot tensor. So eta is this function here. Gamma dot the tensor for startup of steady shearing is what? Sigma dot, yeah, this crazy sigma dot, because it's a time-dependent function now. So 0, sigma dot 0, 0, 0, etc. Okay? So as always, I'm trying to show you the pattern. When we're predicting material functions, we start with the velocity field, and we plug in to the constitutive equation. We don't really need, it's actually nothing here, nothing new, nothing different from the power law model at this point. If we leave the eta in there for now, we can proceed further until we have to do something different. So the gamma dot tensor is 0, sigma dot of t, 0, sigma dot of t, 0, 0, 0. And so what's the magnitude of gamma dot?
Sigma dot t.
Sigma dot of t. Okay? So now, in order to get the stress tensor, we're going to need that eta function. So we've got tau equals minus, and then we just copy it from the test. It says tau naught over the magnitude of the rate of deformation tensor plus m gamma dot of t to the n minus 1 times gamma dot the tensor. Now the gamma dot of t business looks complicated, but it's only startup, right? So startup has got a very simple time-dependent function. It's 0, okay? And then it's something. So when it's 0, there's no flow. So we don't actually, there is a little problem there because it's 0, it's in the denominator. But that's not really even the important part of the flow. The important part of the flow is once you get going. So we know that the stress, no matter what the equation says, we know the stress is going to be nothing until the flow goes. Okay, so there's just nothing going on until the flow goes. So we're only going to concern ourselves with t greater than 0, at which time sigma dot of t is equal to gamma dot naught a constant. So now we plug in that gamma dot naught a constant to see what this startup function becomes later. And we get the stress tensor equals minus tau naught over gamma dot naught plus m gamma dot naught to the n minus 1 times 0 gamma dot naught 0 gamma dot naught 0. And so once again, we get psi 1, psi 2 are 0, which we expect for all generalized Newtonian fluids. And eta plus is equal to minus tau 21 over gamma dot naught. What did you say, Brian?
You have the gamma dot naught inside the gamma tensor, so it's just the function we're given for viscosity.
That's right. It just turns out to be the function we're given for viscosity. There's a minus sign and there's a gamma dot naught, so those cancel those two parts. So we get tau naught over gamma dot naught plus m gamma dot naught to the n minus 1 for t greater than 0. Now to sketch that, which was a bonus problem, when sketching these things, I sometimes think that you're thinking back to some sketch I made before and trying to figure out which of those sketches I made before is this one. Try this instead. Try looking at the equation and thinking about what is varying. So this is eta plus as a function of time. And the time dependence, there is no time dependence here. Here's the time dependence. It's just an issue of what happens after time is greater than 0. So we don't have to worry too much about time dependence. How about rate dependence? Well, the rate dependence, so this is stepping up at time t equals 0 to some constant. There is no time. This is a function of time. There is no time here So it must just be a constant with respect to time. Now, so it does vary with gamma dot naught, however. Okay? So if gamma dot naught is 0, we get that it's equal to tau naught over gamma dot naught. If it's not gamma, so that means for very, very low gamma dot naught, it comes to some value, tau naught over gamma dot naught. That's the lowest it can become. And then as you increase gamma dot naught, you add this term, okay? You add this term. And this term says, depending on what n is, and n in these models, I haven't said, so this would be up to you if you were sketching it. N is usually less than 1 in these shear thinning type models. So if we pick n equal to 1/2, then our viscosity function is related to tau naught over gamma dot naught. Oh, actually, I missed this part here. I said that when gamma dot naught is 0, it's equal to that, and yet this is becoming big. So this is wrong, what I just did. This is wrong. Because there's gamma dot naught in 2 places. So my mistake there. I have to start that thought process over. Plus m gamma dot naught to the minus 1/2. So if this were just the power law model, and I were just doing steady shear viscosity or this plateau level, so log eta plus at long times, t greater than 0, versus shear rate, it would be just like a power law model. M gamma dot to the n minus 1, and with n less than 1, you would get a shear thinning type of a model. And so this says, depending on the shear rate, add a decreasing amount of this, whatever tau naught is. So if I pick 1 shear rate, I've added some quantity, so that shifts the whole curve up a little bit. Okay? And as I increase the shear rate, the effect of this addition is to add a little bit less and less. Okay, so if I pick a shear rate, this portion of the curve is this. At this shear rate, I pick some tau naught, and I divide it by a small number, and so I add a big amount. Halfway down, I get this portion of the curve, and I add, instead of, let's say this gamma dot is 10 times bigger, it's going to be 1/10 as much. So add 1/10 of this distance. And if I go again a factor of 10 higher in shear rate, then I'm going to add 1/100th of this distance, so I'm not going to see any difference. So what I'm going to get is a slightly curving, I'm going to get a line that changes that slope. So this is the curve for tau naught equals 0, and this is the curve for tau naught not equal to 0. So you can reason your way through. That was all bonus material there. But you can reason your way through these plots. Sometimes your reasoning's faulty, as I proved right there. But it's just a matter of looking at the parameters and sorting out how they're affecting the curve you're trying to plot. Okay, and then there was one last problem on the exam, which was a steady flow problem. An incompressible power law, generalized Newtonian fluid, flows down a long, wide inclined plane as shown below. The film thickness is h. The density is rho. The power law parameters are m and n. Calculate the velocity profile. Okay, so this would be a problem solved in rectangular coordinates. So no tables given. So this one's okay, right? Am I right that this one's pretty okay? I would give you, this was what was given that year, useful formulas. Here's the Navier-Stokes equation. Here's the equation of motion. So this is a steady unidirectional flow. And you would need to write the gravity vector. You would need to write the stress tensor. And you would need to write this pressure gradient. Okay? So this exam, by the way, is on the web. So you can print it out yourself and give this problem a try. And come see me tomorrow if you have any trouble with it. So let's look back at the balance of the exam. The exam was a few problems. This was a problem on the standard flow chapter, asking about the symmetry. This problem 2 was all on material behavior from the sheet that I gave you. Problem 3 was on the whole one piece of the task of predicting material functions, which was calculating the magnitude. Every time we do the generalized Newtonian fluid, we need the magnitude of the rate of deformation tensor. So that one was number 3. Problem 4 was an actual prediction of a material function, and problem 5 was a flow problem. So that's typically the structure I use for the exam. Any other questions on what might be on the exam tomorrow? I have office hours right after class as well. Okay. I hope I didn't beat a dead horse there. So let me take the last 7 minutes of class to talk again about the Maxwell model. Let me remind you what we're up to with respect to the Maxwell model. We have developed this new model called the Maxwell model. Here it is in 2 forms. This is the differential equation version, and this is the integral version. I don't expect you to memorize them. That's not necessary. But I'd like you to be able to do the kinds of things that we just talked about for the test. I'd like you to be able to predict material functions, especially with these 2 models. Now, the differential version we're not typically going to use. We're going to use the integral version. And to make predictions of material functions with the integral version, it always involves a time integral. But other than that, it's the same as dealing with the generalized Newtonian fluid. We need, for the flow that we're interested in, we need to write down the rate of deformation tensor and then carry out this integral. So we did that last time with steady shear, and we predicted that the steady shear viscosity was a constant, and the constant that it was equal to was that constant eta naught that appears in the model. Okay, so we put in 0, gamma dot 0, gamma dot 0, 0, 0, 0, 0 in here for the gamma dot tensor. Only the tau 2,1 and tau 1,2 terms were non-zero, and we had to do an integral of this exponential, which was straightforward. Lots of stuff canceled out, and we got that tau was equal to eta naught times gamma dot naught. And when we put that into the definition, we got this. The other thing I did was I went through the calculation for the step strain material function. Same drill. We write the gamma dot tensor from the velocity field and predict the tau 2,1. And in that case, we had to do, again, some integrals because the time dependence was more complicated for the step strain case. But because the sigma dot tensor, sigma dot function here was 0 for much of the time, it came out a little bit simpler. And then we had to take the limit as epsilon went to 0 and use L'Hopital's rule. So that result was that the startup function should look like this kind of an exponential. Oh, excuse me, not the startup function. We did this one. The step stream function is this exponential decay. And I showed you what that looked like when we plot it, and I showed you what it looked like when we compare it to real data. And that's where we were at the end of class. Now, I want to adjust this model to make it a better fit. So in asking the question, how to improve the Maxwell model fit to G of t, how can we improve that fit? And the answer to that question comes from looking at this fit itself. So this is a fit of this function, G of t equals eta naught over lambda e to the minus t over lambda. We can also write this as G e to the minus t over lambda, where G is equal to eta naught over lambda. That's a very common nomenclature. Now, looking at the prediction, G determines the height of the function. So this value right here is G. So looking at this red curve here, this is the value of G. And then right about here, you see where this is, where t is equal to lambda, that's t over lambda equals 1, right at the knee is determined by what lambda is. So right about here, this time is equal to lambda. So what that means is when I look at the comparison with the data, if I lowered the G that I'm using here, lower, 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 and then maybe shift it to the right, which would be increasing the relaxation time, I could get this curve to match maybe just this portion of the curve. Okay? I could lower it down and shove it off to the right and get it to match this portion of the curve. Or I could lower it down and shove it to the right and get it to fit a little better this portion of the curve, or this portion, or if I made G equal to what looks like the plateau here and shoved it to the left, I could make it hit the G just right, but it would dive off too early. Now, so that means that I can't pick a single value of G and lambda to get a good fit, but I picked 4 or 5 different ones that fit different regions of the curve. And what I'd like is some way to add those up. This is possible by saying that instead of having a single Maxwell model, tau equals minus the integral from minus infinity to t of eta naught over lambda e to the minus t prime over lambda gamma dot of t prime dt prime, that's a single one. What if I wrote this is just contribution number 1, and what if I added a whole bunch of contributions to get the total stress? So what if I change this to eta sub I, change this to lambda sub I, and wrote, I don't know, n equals 4 different expressions for stress, so that I would be writing different expressions for stress for different relaxation times. That would be a way of splitting up the relaxation into different sort of modes. And that's summarized on this slide. Here is, I use sub k in this case. Let me write the stress as a sum of contribution, linear sum, okay, a linear combination of a whole bunch of stress contributions that are at different relaxation times and different, this together would be different G's. All right? We can plug this tau sub k in here, change the order of the integration and the summation, and I get a new model which is called the Generalized Maxwell Model. Now, whenever we have a new model, we can do predictions. We can predict it for steady shear flow, and we can predict it for step strain. Okay? So that's what I'm going to do on Wednesday. I'm going to start with this Generalized Maxwell Model, and I'll put in the steady shear flow material rate of deformation tensor here. And you can maybe see what's going to happen. I have to integrate over this summation. It's not that hard. And then I can do it also for the step strain, also not that hard, although, you know, it's very similar to the previous calculation, but we have to deal with just this separate integration sign. And then what we get the prediction at the end of the day, we'll discuss those and see how I already showed you this peak. I'll show you that we can succeed in really nailing our Maxwell model. And it all comes down to this decision to break up the stress into these different contributions. Okay? So see you tomorrow. Brian, what time did we say the exam was? At 6? Okay, that sounds good to me. You know what? I don't think I got a room yet. I think I forgot to get a room. So I'm going to try for 211 in the Chem Sci building. But check your email for that. That's my mistake. I apologize.